This is Lab 5, Create Your Own Adventure Lab. I decided to analyze the motion of a falling slinky with a tennis ball attached to the bottom. The objective of this lab was to utilize Hooke's law in conjunction with the momentum principle, or Newton's second law, to analyze the motion of a tennis ball attached to a stretched slinky that is dropped from static equilibrium. Then, a computer model can be created to accurately predict the motion of the ball and the slinky. A quick overview of the results. The tennis ball remains stationary, levitating for 0.4 seconds, or approximately 0.36 seconds, just as in the video, until the top of the slinky compresses fully and hits the bottom, forcing the ball and the slinky to fall down to the ground. The computer model accurately predicts the observations. So, things I considered during the making of this lab were: does the tennis ball at the bottom of the slinky stay stationary, just like in the video? When the slinky is released, does the tennis ball fall first? Or does the top of the slinky fall first? Or do they both fall at the same time? Or do the top and bottom meet in the middle and then fall? So in order to predict the motion of the tennis ball that is attached to the bottom of the slinky, we need to specify the net force acting on the system by accounting for all the interactions of the ball with the surroundings. This includes both the weight force, negative mg, and the spring force, negative ks. At the beginning of the video, the ball is hanging motionless. When the slinky is released from rest, the ball remains stationary while the top of the slinky compresses downward towards the ball. You can see this here in the slow motion video. So after analyzing the video in Tracker by setting the length scale to the diameter of the ball, which was 0.067 meters, and the coordinate axes, I rotated it by 1.5 degrees to the right, and stepping through each frame in the video, I was able to create a spreadsheet of x and y positions of the ball and the top and the center of mass of the slinky. This file was read into my code and compared to the motion predictions of the computer model that I created from the initial data of the mass and spring. At the time of first observation, t equals 0, the mass of 0.0567 kilograms, which is the mass of the tennis ball, is at the position 0, negative 1.08 meters, and has an initial velocity of 0 meters per second, because it is released from rest. Using this information and the graph, I was able to calculate the time of levitation, which I found to be 0.36 seconds. In order to be accurate, I also went through the time steps in the video to find this value. I also found the stiffness K, which I found from an online source for characteristics of a metal slinky, and found it to be 0.8 newtons over meters. Another variable that I needed to calculate was L0. L0 is the relaxed length of the spring and can be calculated under the assumption that the gravitational force is equivalent to the force of the spring because the spring was in static equilibrium. I found L, the stretched length of the slinky, and L0, the compressed length of the slinky, by using a website that specified the characteristics of the metal slinky. L was found to be 1.1 meters and L0 was found to be 0.05 meters. Taking these calculations and inserting them into the Python code, as well as applying Newton's second law to predict the motion of the mass, we can compare the computer model of the motion of the mass with the observed data. The fundamental principle used in this lab was the momentum principle, which is seen here. Vf equals Vi plus F net over m times delta t. And this principle can be used to find the velocity and position of both the tennis ball and the spring. So when I run the code, the blue ball represents the top of the spring, the red ball represents the tennis ball, and the yellow ball represents the origin, which was the point of release of the slinky. And then the black arrow is representative of the motion of the ball and slinky system once the spring has compressed fully. While the weight force is constant, the spring force gets smaller as the stretch gets smaller, according to Hooke's law, which is Fs equals negative k times s, which is the stretch. This directly affects the net force, which is calculated by F net equals the tension that was counteracting the weight force goes away, and solely the gravitational force affects the ball and slinky system. Throughout the drop, the center of mass is always falling at a steady rate. This can be seen from this graph of the y position of the fall of the slinky. So the blue line represents the center of mass. So the center of mass, as I said, is always falling at a steady rate, while the tennis ball remains stationary until the spring force is decreased and then falls with acceleration g. And the top of the slinky falls at an increasing rate with acceleration g. So, in conclusion, the tension of the slinky, the spring force, counters the weight of the tennis ball. This causes the tennis ball to seemingly levitate because it does not know that the top of the slinky has been released until the spring force decreases as the stretch of the slinky decreases. Once the top of the slinky hits the bottom of the slinky, the ball and slinky fall to the ground together as they are acted on by the gravitational force alone. Thanks for watching.